Lesson 4.1, Congruence. Some corporate logos are distinct because they make use of repeated shapes or patterns, as you see here. Bolt Company wants to update their original logo. Use the pin tool over here to make 2 new versions of the logo. Version 1 should use the original image and a reflection of it. Version 2 should use reduced copies of the original. So grab your pen. I'm going to be terrible, and that's okay with me. If it's okay with you, just don't look, do it yourself. So I'm going to go like this, kind of copying the image as terribly as possible. Hopefully you can recognize that. And then it says version 1 is the reflection. So here's my original. Let's see if I can do this reflection. Down, over, kind of out, in. Okay, that's pretty bad, but that should be kind of straight like that. There's my gorgeous bolts or lightning bolts. But then it says version 2 wants a reduced copy. So reduced copy of the original. It doesn't necessarily say it wants to use the original. So I'm going to just start by making a small copy. Tinier version. That's terrible, but you get the idea. And then I'm going to make a smaller one if I even possibly can. If you're drawing with the mouse and could do better than this, I am jealous. So it's just making the image. It's getting used to using the tools as well, because you're going to be using those a lot. So original reflection, and then original smaller version. That's called a dilation. So it says, communicate precisely. The owner of the company says, I like your design, but it is important that the transformation image be the same size and shape as the original. So you think about these two that I just drew. Which one of those has the same shape and size? What would you do to comply with this owner's requirements? What other things could you do besides what I just did to comply and make sure it was the same size and shape? Example 1, understanding what congruence is. It says, suppose that a rigid motion. Now, the things that we've talked about with rigid motion in the past topic were reflection, rotation, and translation, where it just moves the shape. It doesn't actually affect the shape. It doesn't change or manipulate the actual shape. It just moves the shape. It says, why does that show that 2 figures are congruent? So why would moving it around show that they're congruent? So that's what we're going to talk about. So if you look at this first polygon, ABCDEF has the following lengths and measures. So it's telling you, here's the lengths of each of the sides, and it wants you to do rigid motion. So here's the composition. First, do the one that's on the far right. So reflect around across line L. Here's line L. I'm going to reflect, and it ends up over here. Then translate to -5. So +2 down, -5. So it says all angles of the figure are still right angles. All the side lengths haven't changed. That is a composition of a rigid motion. And it says basically, if you make a rigid motion, it's not going to change the shape, but it relocates it. Therefore, they are congruent. So a movement keeps the shape. That's congruence. And it's just a rigid transformation that keeps the size or the side lengths and the angles preserved. It means they keep those side lengths and angles. A 90-degree rotation about the origin, these 2 triangles, are the triangles congruent? If you rotated this one 90 degrees to become this one, would they be congruent, yes or no, and why? Here's a big concept, congruence. Now, this definition I am not a huge fan of because it says figures that have the same size and shape are said to be congruent. The way they wrote it isn't exactly true. So let's say this is a triangle, and it will say it's 4 square units, but it's a triangle. But what if I move this triangle a little bit different? See if I can make this triangle. Just made it like more obtuse. It's still a triangle, and let's just say it was still 4 square units, but it's obviously not congruent to this original, right? So it doesn't have to be same size, 4 square units, triangle. That's same size and shape, but that doesn't necessarily mean congruent. You have to have the exact same angles, same side lengths. You can't just say triangle that's 4 square units. It has to have all the same angles and all the same side lengths. So keep that in mind. This is true, but it's kind of, it's not the best definition. Two figures are congruent if a rigid motion can map one of them onto the other. So if I can move this triangle ABC and do reflection, rotation, or translation, and I end up on the other shape, then that is telling me, then yes, those two shapes are congruent. To verify congruence, it says, given these triangles, these are congruent. There's that symbol, the equal sign with the little squiggle. They are congruent triangles. What composition of rigid motion maps triangle XYZ to ABC? So you have to figure out, how do I get this triangle over directly on top of triangle ABC? Now, I want to point out something. This is really important, especially in the next couple lessons. Point X, point X is the first point mentioned in this triangle. That means the corresponding point is point A, because that is the first letter in the triangle. Point Y is the second, so that matches up with the second letter here, and Z matches up with C. So for example, if I had a shape that I couldn't really tell exactly which points matched up, I use this congruence statement. That's what this is called, like a congruent sentence or a congruent statement, and use the order. So that means point X right here matches up with the first point in this statement, point A. And in this case, they actually are right angles, so it's a little bit easier to tell. But maybe this was an isosceles triangle, and it wasn't very hard to tell, like, does Y match up with B, or does Y match up with C? Sometimes it's not easy to tell, so you have to use these congruent statements. Okay, what the solution says and what I think happened could be different, and it could be the same for you. So let's just say I map this triangle by first translating it over here. Point C, I translate to point Z, I translate to point C. Okay, and then I would rotate it 180 degrees. So visualize translation to point C and then a rotation. But if I look at these answers, that's not what they say. But it still would work, so be aware of that. So first they say I'm going to rotate 180 degrees around point Z. So I'm going to take this, and this goes step by step. So this little icon down here, it moves at first step, rotating 180. Boom. Whoops. There it is, 180. I said to rotate last. That's okay. So rotate 180, and then I'm going to slide it over. Let's see how many. 1, 2, 3 points. So I'm going to go here. 1, 2, 3. And it's exactly lined up. It's almost like you can't see it at all. So this is the order they used. They used rotation first and then translation. So you could potentially be totally correct on your composition of transformations as long as it maps the original or the pre-image onto the image. So that's what the book did. Just don't stress about it. The order could be different. Try it. You're going to use this graph. Given this graph, what is the composition of rigid motion to map GHJ onto KLM? So you're going to figure out what steps would you use. And again, it might be a little bit out of order than what they say, so don't stress too much. And they even say, hey, what's another way you could do it? Could you change the order and it still work? Could you use a totally different transformation? So if you use like reflection one time, could you use rotation or translation another time? So you want to see if there's another way. Identifying congruent figures. You're going to be given different shapes and you have to determine if they are congruent or not. So there's a couple ways to do this. These ones, actually, they all look the same to me. They look pretty close to the same. So if there's an obvious difference, then you can be like, oh, they're not congruent, not even a question. But sometimes they're hard just to tell. So you would have to take triangle ABC, just start with one of the shapes, and see if there's a way to transform, rigid transformation, onto these others. Let's see what they do. Step 1, translate, 3 down. So they're going to take this triangle, it's 3 down. And then it looks like they're reflecting, so it even tells you reflect across this line, -4. So if I end up here and go here, hey look, LKJ, LKJ, this one worked. So now can we figure out how to move this original or even this red triangle to get to this other triangle, that third one that's over here? So we look down here, whoops, and say, The composition of the rigid motions, translating 3 down and reflecting over M, it works. So therefore, they're congruent. But if you look here, it's saying AC and EG are not even the same size. So let's go back to the original. AC and EG. From here, they look the same size to me. So if I rotated and I physically rotated on a graph, you would say that they wouldn't line up. But this is how you can tell. Think of the Pythagorean theorem. So how much you go over and up, there's your right angle. And then the hypotenuse would be the diagonal. So diagonal, hypotenuse, 1, 2, 3, 4. So I go 4 horizontally, 1, 2, 3, 4, 5. So this length of AC, you could figure out using the Pythagorean theorem, 4, 5 for the A and B. So let's try this here. This length, 1, 2, 3. From E to G, the horizontal distance is only 3. 1, 2, 3, 4, 5, 6. So if I did the Pythagorean theorem, 3 and 6, a squared plus b squared, I would get a totally different C than I did 4 squared and 5 squared. So even though visually when I looked at this, they totally look the same, you have to be careful of the size. So you might need to count. So it's basically saying they're not congruent because they're different sizes, therefore they would not line up with each other. So try it. You're going to do basically what we just did. So you're going to figure out if these are congruent, A, B, C, D, E, and J, K, L, M, N. If so, you're going to describe how one got to the other, and you're going to see how it works, okay? It doesn't actually mention this, but this might be helpful in the series or the composition of functions. You might not use it at all. Now you'll use it. So here's the second part. You're going to use, is this triangle or this polygon congruent to this polygon? To determine congruence. So there's a couple ways you can do this. If you can find the rigid motion that maps the original pre-image onto the image, then it is congruent. So are these pair congruent? Is there any way you can make this end up on there? I'm not going to tell you the solution. But can you visualize a rotation, a translation, or a reflection, or a composition of those to get this shape to that shape, or vice versa? How about this one? Look carefully. The sizing, the angle measures. I want to see if you can figure that one out. Now this one, I'm going to point out. So look at this. Pink, blue, green. Pink, blue, green. And then you have a purple and orange next to each other, next to the green. Then you have this kind of yellow mustardy color in between, which you still have. And then this blue that touches that pink, which you have. So it looks like the order of all these rectangles are perfect. I just have to figure out how did I get from one to the other. So try to figure out rotation, reflection, translation, or a combination of those to move one of them to the other, or back and forth. It doesn't matter which way. Can you figure out these? Can you map them on? If this was a test or a quiz, I might physically trace the picture and then see, can I rotate, reflect, translate, and put it onto the new figure? And you can do that. You can actually physically trace something and see if they map onto each other. And this one, I'm hoping, is a little bit more obvious than the others. Okay, example 5. Applying this congruence. So a boat builder plans to connect 2 pieces of wood by using a puzzle joint. It actually looks like this. You can see like the zigzagging of it. Okay. And it keeps the water out. So it like kind of fits together almost like groove and teeth, and it like fits in and it slides in perfectly like that. Okay. So for a successful joint, each unit must be congruent. So if this side and this side, like a puzzle, they have to be matched up perfectly. So it says, given unit A, what composition of rigid motions maps unit A to unit B? How do I get from unit A to B? And you would describe it. Here's another one. Is unit C congruent to unit A? If so, how would you map unit A onto unit C? You need to describe that. Here's the overall message. The concept summary. Congruent. It's if 2 figures are congruent, the composition of rigid motion maps one figure, the pre-image, onto the other the image. So if I look here, here is the notations. They are congruent because since the reflection of the original gets mapped on to the new. So since there is a rigid motion, these will be congruent.